Today we're going to be doing a pretty interesting geology investigation. We're going to be learning about how rocks and sediments make sedimentary rocks. And we're going to be making a model using sediments to see if we can see how rocks form layers. I always start our investigations with our worksheet. Our name, my name, and your name is, go ahead and put your name on yours. Today's date, and it's the fourth grade, okay? And I always start with a question about something you observe. Well, I'll tell you, Indiana is pretty famous for something that I observe, and that is the rocks and the layers of rocks. Have you ever driven around in southern Indiana and other parts not too far from here, and every once in a while the road will go down a hill, and if you look on the side of the road, you'll see these really interesting layers. And the funny thing is, the layers are the same on one side of the road as they are on the other side of the road. So let me show you what I mean. Let me draw a little picture right here of what I'm talking about. I know that sometimes you'll see layers that kind of look like this, and here's another layer. They're not always the same, but they always kind of, and then up on top here is where sometimes you'll see trees, and there might even be a house here on the top, and this is the grass and the surface. So that's, in fact, sometimes you even see people as you drive down. And so as the road goes through here, on that side of the road, you see these different layers. This layer might have round rocks in it, and this one might kind of look like this, and then this one, and the top one might have gravel. And so I see these layers of rock, but the really interesting thing is on the other side of the road, if you look on the other side of the road, and maybe there's even trees on this side too, and people standing, look, hey, you'll see the same layers. Like this one might have round rocks in it, and with the grass up here. And so what's interesting is that if you find this layer here, that same layer is over here. And they're in the same order. They're in the same order. Pretty interesting. And it got me thinking about these layers. You see, Indiana is famous for a type of layered rock. We're famous for limestone. Limestone is a sedimentary rock that you find in Indiana. It's close to the surface. It's a layer of rock close. It's bedrock. Take a look at the back of your worksheet. Here is a map of Indiana where they've scraped off all the dirt, all the sand and gravel, and these are the bedrock, the limestone, the bedrock that's deep underneath the ground. In fact, if it's even under your school right here. And these layers, now they've been color-coded so you see them better. They're not really this color. Scientists use maps and colors to help explain ideas, but they are in this order. Down here, the pink are the very old, and the green are the very new. So we have from new to old going up and down, and these are bedrock limestone. So the limestone you see here in Indiana, it's famous because it is a good material to build with. Indianapolis is filled with buildings made of limestone. And not only is Indianapolis, but in Washington, D.C., the Washington Monument, the Lincoln Memorial, even the Pentagon is made of Indiana limestone. I took some kids to New York City, and we stopped to see the Empire State Building made of Indiana limestone. So we're kind of famous for our sedimentary rock. Let's turn this back over, and I wanted to show you. Let's start with a question about all of this. And I always like to start with the question. So you might want to write this. This one's a kind of a short question. Teachers, you might want to put this on the board. And the question is, how do sediment layers, sediment layers, form sedimentary rock. That's our question. How do sediment layers form sedimentary rock? We've looked at our question, how do sediment layers form sedimentary rock? We need to now have a hypothesis, and this hypothesis is kind of long. So we will go ahead and write it, and it goes like this. If sediments move by gravity and water, then if sediments move by gravity and water, then they settle because sediments sink to the bottom when water stops moving. If sediments move by gravity and water, then they settle because sediments sink to the bottom when the water stops moving. Go ahead and write that on the wall, on the board, and write it on your worksheet. We have a question and have a hypothesis. Let's look at some of the control variables that we're going to talk about. All right, the control variables are the things that we want to keep the same. And what we're going to keep mostly the same today is we're going to use water, and we're going to use sediments. And everybody's going to use the same water and the same sediments. And the sediments are, in this order, we're going to use gravel, peat moss, soil, and sand. So we're going to use water and sediments, and the sediments we're going to use are peat moss, soil, and sand. Now when we talk about dependent variables, what is measured, we hope we're going to measure layers. And what's the one thing we're going to change? We're going to change the force of moving water. The force of moving water. So it's give you a chance to get caught up on that. Indiana has sand dunes that were brought here by glaciers, and it has all types of sedimentary rocks that are very, very old, and it has sediments and clay and sand and gravel. In fact, a lot of things were eroded from Canada, which is now Canada today, and brought to Indiana. And that brings me up to another concept that we're going to talk about today, and that's erosion and deposits. Check out your worksheet right here. Here's a picture, and here are the new words I want you to add. It says, where a river flows fast, it erodes. But when it slows down, it deposits its load. So here's a river, and this is moving because of gravity. Gravity makes things go downhill like rain and water, and it erodes. It's called erosion. Erosion, which erodes. And that I like to put a minus sign. And then it deposits, which is a plus sign. So whenever you see things that erode, that means it's being taken away. And when you see things that get taken away, they have to be deposited somewhere. So take a look at this drawing right here. All right, check it out. Where a river flows fast, it erodes, but when it slows down, it deposits its load. So I'm going to give you 5 seconds. Where do you see erosion and where do you see deposit? 5. Go ahead and mark an E for erosion and a D for deposit. 4, 3, 2, 1. Well, I'm going to see erosion up here and deposit down here, because here it's being eroded away, and then here it's being deposited. Okay, so erosion is when things are moved away, and deposit is when they end up being placed somewhere else. Now, there's a good way for me to remember that. I have my wallet here, and when I get money, I deposit my money in my wallet. Nice deposit. I lay my wallet, and my daughter, she comes and she erodes my money and takes it to the shopping mall where she buys nice gifts, and she deposits the money at the mall. And hey, you know, this is not really going too good for me. I deposit, she erodes, she deposits it at the mall. Well, you get the idea. Erosion is when things move away, and deposit is when you put things back down. But you know, rocks, when they move, and they move in a river, they get banged around and they break. And there's a name for that, and it's called weathering. Weathering is when a rock moves through and starts making smaller rocks until finally you have a whole bunch of rocks. And so you start with one, and it ends up into one big one, and you have many medium-sized ones, and then you end up with many thousands of small ones. The form just gets changed, and that's what happens when a rock moves down a stream. The sediments and things get completely banged against each other, and they turn into smaller sediments, even some things called silt. Hey, check this out if you don't believe me. Look what happens in Indiana when it rains. This last summer, you didn't need a model of eroding water. Record rainfall caused massive flooding in Indiana. So much water rushed through the state that man-made and natural features were changed. All of this water, powered by gravity, created new features on the land. Like this new channel and island in the Wabash River.
And maybe I'm the fortunate one. I still have property, but it's all on an island now.
This farmer used to farm his land, but the flooding was so powerful that it changed this peninsula into an island.
We were located in southern Posey County, right near the confluence of the Wabash and the Ohio rivers. And we're standing right here at the new cut that has been created by the Wabash from the floods back in mid-June. As you can see behind me, the new channel, the Wabash still has its existing channel, but then also there's a new channel that's cut through behind me that cuts all the way across this peninsula and then reconnects with the Wabash on the other side.
The floods washed away millions of tons of earth, rock, and gravel. Indiana exported a lot of sediments into the Ohio River. Indiana's sedimentary rocks provide a window into the lives of plants and animals of prehistoric time. Fossils are found in sedimentary rocks. The more there are sediments, the greater the chance for fossils. Now, if you take a look, this is a coal mine I visited in southern Indiana, and at the top you can see some sand and gravel and just a few, maybe some shale, but as you get down, you see these different layers. And some of these layers, like that black layer in the middle, is actually a very valuable sedimentary rock called coal that used to be part of a forest. You can see that water and gravity move lots and lots of sediments. And when the water slows down, the sediments fall down. And basically, that's what we're trying to prove today with our experiment. So we've done our research, we've done our background. It's now time to start our investigation by making a model. All right, so here's what I want you to do. Turn your worksheet over. You have your bottles ready. You have your sediments ready. We're going to do this step by step, and we'll see if we can prove our hypothesis with some data. First thing I want you to do is take a look at your bottle and draw a model or a drawing of your bottle. Make sure you have a lid on yours. Okay, and doesn't have to be exactly like a bottle, but try to make a big bottle. Okay, here's my bottle. Here's my bottle in real life. And it has water in it, so I'm going to go ahead and write water. Label it. Go ahead and make your drawing. Okay, the first thing we're going to do is I'm going to take the lid off of my bottle. And I'm going to put a funnel, my funnel in it. We're going to pick one of our 4 sediments. And the first sediment I'm going to use is actually one of my favorites. It's kind of famous, if a sediment can be famous. I'm selecting gravel. Gravel. And you might think, well, Mr. Crosslin, why is gravel so famous? Well, I'll tell you, take a look at this gravel. All of these rocks are round. Now, nature did this. As these rocks move back and forth across each other in water, they get weathered and pieces break off and they make nice round rocks like you see right here. And that's kind of famous because when you see gravel, if it's round like that, it's been in water a long time. Now, a couple months ago, there was a very famous science discovery that you may have heard about. NASA sent a rocket ship to Mars several years ago, and it took 3 years to get there. And as it came close to Mars, down came a Martian lander called Curiosity. It's like a robotic space lab. It landed with parachutes and rockets, and it opened up and started sending pictures back. And as it traveled and explored and tested, it saw something very interesting. In part of the dirt, there was a layer of round rocks, a layer of gravel on Mars. Now, what you know is that for rocks to be in a layer and for rocks to be round, there must have been moving water on Mars. And so that was the first time that scientists have found evidence that there really was moving water on Mars. And they found it because they found rocks that looked like gravel. So the first thing we're going to put in our sediments are some sediments of gravel. Now, look, my water's clear. And we'll see what happens when I put this in here if it stays clear. So I'm going to do it, and then you do it. Oh, gravity's doing its thing. Going to the bottom. And look what happened. Not only did the sediments go to the bottom, but my water turned cloudy. And there's a name for that. My gravel sediments, my round gravel sediments went to the bottom, but some of the dust from the weathering, which is on those rocks, now makes the water cloudy. There's a name for both of those. Right now, go ahead and on your drawing, I'm going to write all my round rocks, go here at the bottom. And as long as they're rounded, I don't care what they look like. And so we have round gravel, okay? And all this stuff floating around is called silt. It's a very, very fine, it's really small particles, and it takes a long time. See, the gravel went down quick. Silt takes a long time to go down. Okay? Make your drawing. We're going to add our next one, and our next one is something called peat moss. Now there's a new word for you. Peat moss. Moss is a plant, and this used to be a plant that grew in the swamp, and when it died, sank to the bottom, and over years you can still see small pieces of material in there, twigs and part of the moss. It's kind of dusty, so be careful that this is really fine. It doesn't have a lot of mass to it. The gravel went down quickly. See what happens when I add the peat moss. Here we go. Here's my first. Oh, look what it did. It stayed right on top. Let me add a couple spoons of peat. Be careful, it's kind of dusty. And it stays on top. A little bit is down, but most of it's staying on top. Go ahead, add your peat, and then make your drawing. And label it peat moss. And for some reason, it's staying right now at the top. Next, we're going to add soil. Soil is pretty famous here in Indiana because we have some really good soil that farmers use to grow their crops. And the soil you see here actually is made up of some living and some non-living parts. Some living and some so I see parts of twigs and leaves, but also in here, and it's hard to see, there's sand and rocks and gravel, and all the plants and animals that used to live and walk and die and decompose is mixed in this soil. This is about an inch of soil, and it takes about 10,000 years for 1 inch of soil to form. So I hate it when it rains and all of our soil leaves Indiana, gets washed into the streams, down the rivers, into the Gulf of Mexico. We export more soil than almost anything. So soil is very important. I want to put 3 or 4 spoons of it in our sediment and shake it around. And I'm not going to draw this quite yet. So we have our soil. Add the last sediment, which is sand. I love sand because who doesn't like to walk on the beach and feel sand under your feet? See, sand is formed from a hard rock called quartzite that gets weathered and turns into small grains. So when you see sand like this, it has been crushed and moved by wind. That's called a sand dune when it piles up, or by water along a river or in the ocean, back and forth, and it just keeps weathering and weathering and weathering. Some sand is very fine and some is coarse. It all depends on the type of rock or how much it's been weathered. So you take sand and squeeze it back down, it turns to sandstone. Sandstone gets broken up back into sand. There's a cycle where it goes round and keeps forming. Let's add sand to our sediment bottle. It's the last one. Something interesting is going to happen. The sand is not going through the layer right now, and so I might end up getting some kind of a little underwater avalanche. Move this a little bit closer so you can see it maybe. Nothing happened. Oh, the water's starting to soak up. I'm doing this slow. You might want to do yours slow just to see what happens. And there we go. There's actually underwater avalanches just like that. Okay, I put enough sand in there. And now things are starting to move around. Okay, I see some layers here, but you know, this is only part of it. Go ahead and put your sand in, and then put your lid back on. I have here my bottle with my lid on, and now the fun part comes, because here's what I'm going to do. I'm going to take this, and now it hasn't really, not much energy's put into it. Remember our hypothesis, we're going to change the force of the moving water? So I'm going to shake mine, watch what I'm doing, and you hear this. This is what it sounds like when a fish is in a stream with water. I'm shaking it, and then I'm going to stop, and we hope things will settle down. So I'm going to shake it. 1, 2, 3, 4, 5. I don't know if you could see that, but look what happened. The gravel went to the bottom, and then the sand, and now there's still some stuff moving. So once I've shaken this, I'm just going to let it set for a couple hours to see what happens. So I'm going to do it one more time, just so you know. You only do it once, get a nice shake. And I'm going to show you up close what happens when I stop. Here we go. See how the sediments fell out? The heavy ones first. And now I'm going to leave that for at least an hour or so without touching it to allow the sediments to settle. Go ahead, put the lid on, add some force to your sediment bottle, then set it aside. Before I do this last demonstration, let me show you a small segment about what a teacher did with his class in sediments. After talking to Nelson, I wanted to share my newfound knowledge with my friend Chuck Calley from Chapel Glen Elementary. When I arrived, Chuck was already doing a cool experiment controlling runoff water.
What we have is we have 3 control groups to where we had the same composition in each creek bed. So we had rock, sand, and they actually measured it out in volume, what materials they were going to add to the riverbed. And then the variable group, they were charged the task of stopping erosion. So I showed them some examples that scientists are currently using through images that I captured on the internet. And they came up with, okay, we're going to put cloth down on top of the soil, use big rocks, or we're going to build a clay wall. And so we're testing which one of these 3 variables will control erosion the best. Right now we're doing science. We have controls, we have variables, we're measuring the data that we collected, we're analyzing the data, and this is doing science.
Do you know how it's going to turn out?
No, I have no idea, so we'll see.
Chuck was using a model to explain how water can shape Indiana. A model is used in science to explain something that is not easy to reproduce. A big part of teaching science correctly is not giving the answers to your students. Better yet, let them find out what might happen.
If you didn't want your pond being filled up with sediments, would you, yeah?
Chuck's class found that the clay wall was most effective in stopping erosion.
This is science. Try it yourself.
Okay, so you saw how that class investigated sediments, and I want to take a look now at how my bottle is doing. And if you can see, it's starting to settle down. There's still some time. I'm going to leave that for a couple more hours. You know, time is something that geology does very well and very long. So I'm going to try to make one more demonstration that has to do with how sediment rocks are formed, and it's kind of interesting. I hope you'll like it. Let's see, let's check it out here. So I want to start with this map of Indiana with the old rocks here and the new rocks here, and let's see if I can make this very same model of a map like that. I'm going to start with some sediments that are kind of unusual. I've noticed these around Indiana. Maybe you've seen them. Here's my sediments I'm starting with. It's called the bread sediment. Okay? Here's my first layer. All right? On this bread sediment, later comes a new kind of sediment in Indiana. Water moves it down. I call it the yellow cheese sediment. Okay? Gets piled up. Along comes more bread sediment, settles down. And then we have the sediment, something strange, some really strange fossils. You see the fossils in these sediments here? These fossils form, and they form a layer. We get some more silt and gravel, bread sediments. Now, here's my question. What part is older? Up on the top or down on the bottom? Which ones did I put in first? There's a little bit of earthquake right there. The top or the bottom? And I hope you realize that this is new, down here is old. Oh, another flood, and in comes more strange fossil sediments. Luckily, we have more bread sediments coming, and they keep piling up layer after layer. With the old stuff on top, and something weird happened in Indiana. We got this other kind of white sediment, chalky sediments that came in. It was a pretty big flood because here comes some more of it in. Luckily, things settled down with some more sand and gravel. And then we had some really strange sediments coming in. These guys kept on coming and they piled up. Some years they were taller than others, but there was always that old bread sediment coming in. Now, so where's the oldest stuff? Up here on the surface or down, down, down deep in the bottom? The old stuff is, of course, down here on this layer. But then something interesting happened in Indiana. There was just the right climate and plants, and we got this very strange forest that grew in Indiana with certain types of trees and giant dragonflies, and it was a big, hot, swampy area. And for a long time, those sediments piled up here in Indiana, and piled up, and piled up, and piled up, until they died, and all those plants died in the swamp, kind of like peat moss, and then more of these wonderful, strange, soft bread sediments piled up on top. Now, here's my problem. We don't have millions of years, because after millions of years, what happened was these sediments, after time and pressure, they started getting squeezed and squeezed and squeezed down, and the sediments kept getting squeezed with more pressure and more pressure. I don't have a million years, but I do have a few seconds, and I'm going to squeeze it down with giant pressure. And so all of this was squeezed down, and we made these sediments. And look what happened when the sediment layers turned into sediments. They're all squeezed down. Now, you got to believe me, those sediments are still there. You have to believe me, those sediments are still there. If only we had a drilling company, we could drill down and see if they're still in the same layers. You think they're still in the same layers? They are, and I do have a drilling company. Here's my drilling company. It's called the Straw Drilling Company. I'm going to do a core sample. I'm going to use this straw, see if I can drill down. I'm going to drill down and see what I find. So I'm turning my drill, going through one layer, to another layer. It's kind of rocky and bumpy, and I'm going down and down and down until I hit through the bedrock, and I can't go any further. Twist it a little bit and see. Now it's time to pull up my core sample to see what I have in there. And let's see, pull it on up, and wow, check it out. Some of the same layers. I see the coal at the top, and I see some of that strange fossil at the bottom. So I can't wait for millions of years for a glacier, 1,000 years, so I'm going to use a model of the glacier. My wife's electric knife. It will erode or cut away some of the material. Let's see what it looks like. Here we go. Wow, there's the same layers. Here's my core sample. Let me see if I get down to my core. See where my core sample came from right here? Right there. So you can see the layers, how they were deposited, more erosion. Here we go. Now these layers, this is just like that road cut I was telling you about. If I open this up, on one side of the road, you can see on the other side of the road, old at the bottom, new at the top. And across the world, some layers you can find in Indiana, and you can go all the way to England and find other layers just like it. And layers get folded. This is called folding, and sometimes there's actually sometimes they do this, they fault, and they'll break through an earthquake. But right now I'm hoping that that looks like Indiana. But you know what? It doesn't quite look like Indiana yet. Let's see. I still see my core sample. Indiana looks like this. I'm missing something. Oh, I know. The glaciers actually came through, and let's see if we can get this in the shape of Indiana. All right. There's a little bit of a Ohio River. There's the Ohio River. Now I need the Wabash River. Okay. Let's turn it around so I can cut this. Here's the all this got washed down in the Gulf of Mexico. All right, now, hey, that's looking kind of like Indiana. Let's see. The Wabash, the Ohio. The Wabash over here, the Ohio. Oh, you know what? The glaciers did come through, and they cut off the topsoil. And they cut off some of the layers. Does that look like Indiana yet? Well, let's see. It's starting to look a little bit like it. Yeah, there's the glaciers kept coming. Cut through some really old rock until it got way down here. There's some of the oldest rock in the state. And we ended up with something that kind of looks like Indiana with different layers. Looks like we have the coal right here on this side of Indiana. And right now, you know, the only thing that's missing, though, Lake Michigan is right up here. I'm going to have to find a way to put Lake Michigan. Oh, I know. Lake Michigan goes right about, forces that shaped Indiana. Gravity, wind, water, ice, and me eating Lake Michigan. So, I hope you enjoyed today's lesson on sediment bottles. Don't be angry because I ate Indiana. I hope you enjoyed sediment bottles, and check it out. Settle down, sediments, settle down.